Hello students, good evening everyone. Welcome to Infinity Learn by Sri Chaitanya. This is me Surya, your chemistry faculty from Infinity Learn. Hi Arush, good evening. Okay, I hope I'm perfectly audible and visible to each and everyone present over here. Okay, finally we are moving to the one-shot revision for the second chapter, acid, base and salt. We have already covered our first chapter, chemical reactions and equations. Yes. Today we are going to discuss the acid, base and salts. We have already studied the chapter, right? So I'm just giving a brief idea about the complete chapter, including all the small topics in the chapter. So these are the important contents we are going to discuss in today's class. So introduction part for the acid, bases and salts, right? Then what do you mean by the indicators? There are the different types of indicators are present. We will be going to discuss about the types of indicators, their color change and everything. Then we will be discussing about the theories on acids and bases. Based on the acids and bases, there will be 3 different theories are there. So we will be going to discuss these theories. After that, we will be discussing about the different types of compounds based on the salts compound, right? So common salt, bleaching powder, washing soda, baking soda and plaster of Paris. So this is the content of these classes we are going to discuss today. So let us start with the first introduction part. What do you mean by acids? We have already studied, right, what do you mean by acids. So I need your complete support. This is the complete revision class. So just try to respond with me. So as you can see over here, right, these are the compounds in which hydronium ion or the H plus ions can donate. These type of substances are known as the acids, right? So whenever we are discussing about the definition part of the acids, we can say that acids are the substances, right? They are the substances, they will be forming H plus ion or the hydronium ion. Clear? Then only we can discuss about the physical properties or the taste of the acids. Then they are sour in taste, right? They have the sour taste. Then later on many theories were postulated to include the other compounds that were acidic but did not produce H plus ion. So in general we can say that acids are the substance, they will be producing H plus ion. But later on whenever we are discussing about the theories of acids and bases, we can say that acids can be defined by 3 different theories. What are they? 3 different theories. Hi Durgesh, good evening. First is the Arrhenius theory, right? Then Lowry Brønsted concept theory, then Lewis acid theory, right? Lewis acid base theory. Yes. So here are some of the examples for acids. So as you can see over here, in our stomach there will be one acid present, right? Which are they? Is hydrochloric acid, right? Hydrochloric acid. Yes, Arush, you are correct. Arrhenius theory, Brønsted theory and Lewis theory. These are the 3 important theories based on the acids and bases, right? So in case of digestion or in our stomach, we can say that there is one acid present, that is hydrochloric acid, right? Yes, HCl, hydrochloric acid. And this is acetic acid, vinegar, which is commonly used in our home as a preservative, right? Then citric acid. In all the citrus fruits like lemon or in other fruits, it will be containing citric acid as one of the component, right? Then in almost all the painkillers, just like aspirin, we can see another acid known as salicylic acid. Clear? These are just the examples for the acids in our daily life. Yes, CH3COOH is the acetic acid. C2H5OH is ethanol. This is not an acid, right? Arush. Now, what do you mean by bases? How we can define bases? We can define the acids as H plus donors, right? So bases are characterized by their bitter taste and they are slippery in nature. They will easily produce as OH minus ion, right? They will be easily produce the OH minus ion. Yes. When dissolved in water, they are producing OH minus ion and they have the bitter taste or they have the slippery nature, right? Can you please give me any example for the bases? Yes, potassium hydroxide is one of the examples, right? So some of the examples or images you can see here in detergent, sodium carbonate, Na2CO3, right? Then sodium bicarbonate, NaHCO3. This is also known as the baking soda. This is another example for the bases. Then ammonia, as we already know, in the case of fertilizers, we are using the ammonia as the base, right? NH3. Then ENO. If you have any digestion problem, we will be using the case of antacids, right? This is known as the magnesium hydroxide. Clear? These are the simple examples for the bases given here. Yes. Now the next part of the chapter, that is salts, right? What do you mean by salts? So is there any idea what you mean by salts? How salts are forming? These are combined together to form, right? When acids and bases are combined together to form, they will be forming salts by the neutralization reaction, right? We will be going to discuss about the type of neutralization reaction and the type of salts formed between acids and bases, right? Yes, acid plus base is giving the salt, right? Can you please give me any common example for the salt? Sodium chloride, right? Table salt or the common salt which we are using in our home. That is another example. And next one is the potassium chloride, right? KCl, potassium chloride, and sodium sulfate, Na2SO4 is another example for the salt. These are formed by the reaction of acids and bases, right? So depending upon the name of the salts, we can find out the parent acid as well as the base, right? Yes, if I am taking NaCl, is formed by mixing sodium hydroxide plus HCl, right? So this is a strong acid, this is a strong base, so they will be forming a neutral salt. Clear? Now the next part for the chapter is the indicators. What do you mean by indicators? What is the use of indicators, right? So these are some substances which used to indicate the presence of acids or bases, right? Such type of indicators are known as the acid-base indicators. From the name itself it is suggesting, right? It is depending on acid-base. So generally we can say that these are the basic solutions that change color or the order in the case of acidic solution. Clear? I hope you understand what you mean by the acid-base indicators. These are used to detect the presence of acids or bases whenever they change color or order. Now based on the acid-base indicators, we will be dividing these acid-base indicators into three important indicators. I hope you may have idea about that. First one is the natural indicator, right? Okay, I hope the screen is visible to everyone. This is a natural indicator. Second one, olfactory indicator, right? Olfactory indicator. And third one, this is a synthetic indicator. So what will be the difference between these three type of indicators? Or can you please give me an example for these natural indicators? Anyone, please give me an example for natural indicator. They are presenting natural light. Yes, turmeric is one of the natural indicator, right? So what is the color change there? If I am taking turmeric as one of the natural indicator, right? So these are the common examples for the natural indicators. So what will be the color change? If I am taking turmeric as the indicator, what is the color of turmeric in acid solution and basic solution? Okay, I hope you can see the color difference, right? So I am taking turmeric as a natural indicator here. Its original color will be yellow, as we already know, right? So turmeric is having the original color of yellow color. Whenever they are placing in the case of acidic solution, they will be turning to yellow color itself, right? It will be having the same color in the acidic solution. But if you are containing any cloth or anything having the turmeric part, if you are using soap as a base, right, soap as a basic solution, what is happening to the color change? Color will be changes to red or reddish brown, right? Red or reddish brown will be the color change for the turmeric in the case of basic solution. Okay, I hope you understand. Now another example is the hydrangea. This is a flower. As you can see over here, its original color is blue, right? In acidic solution, they are also shown the blue color. But if you are putting into the basic medium, if you are taking any of the basic medium, you can say that the color will be changes from blue to either pink color or purple color. Then another example for the natural indicator is the red cabbage, right? Red cabbage, as we already know, it will be having a red color, almost red color to the acid solution. But if you are putting it into the basic solution, it will be changes its color from red to green, right? Red to green. Then litmus paper, as we already know, this is a common example for the natural indicator, right? So what will be the color change for the litmus paper? For example, if I am taking blue litmus, right? Generally, if you are taking purple litmus for the indicator, so it will be forming blue to red, right? Blue to red in the case of acid solution and red to blue in the case of basic solution. So this part is very important. If you are taking the red litmus, right? If you are taking the red litmus, it will be turned red to blue for the basic solution. And if you are taking blue litmus, it will be changes to blue to red for the acid solution. Clear? Amruta, I have just started the revision here only. We have just talked about what we mean by acids and bases, right? So acids are the substances. They will be forming the H plus ion with the aqueous solutions, right? Similarly, bases are the substance which will be giving OH minus ions to the aqueous solutions, right? Then whenever acids and bases are combined together, they will be forming different salts. So we have seen the examples for acid, bases and salts here. Now we are discussing about the indicators. So what are the indicators? What do you mean by acid-base indicators? How they are classified into different natural indicators, olfactory indicators and the synthetic indicators. So here we are discussing the color based on the natural indicators, based on acidic solution as well as basic solution. The last example is the China rose. This is the flower, right? So it has a light pink color. Whenever it is put in the acid solution, it will be changes to dark pink, and for basic solution, it will be changes to green color. So this is the natural indicators, examples of natural indicators as well as their color change in acid and base solution. Okay, I hope you understand. Now let us discuss in terms of olfactory indicators. So what do you mean by olfactory? Is there any idea about the term olfactory? Arush, is it necessary to contain OH minus ion? So in the case of acid-base indicators, we can say that they are generally basic solution. Maybe they will be containing the OH minus ion. They are the basic solution. They will be changes color in the terms of acidic solution. Yes, olfactory means smell change, right? Odor change, right? So these are the indicators can change their odor when they are mixed with acid or base, right? Is there any example? Yes, it is given, right? Onion, vanilla extract and clove oil. So what will be the smell change there? For example, if I am taking vanilla extract, onion or clove oil, in acidic medium there is a characteristic smell, right? In acidic medium there is a characteristic smell. If I am taking basic solution, if I am adding these substances, it will not have any smell, right? This is the difference between acid and base solution. So we are using these terms as the olfactory indicators. Clear? Okay, Harish, just try in your home neutral solution, right? Water. Just try. Is there any smell change happening whenever you are putting in the onion in water? We need to just identify what is the difference between acids and bases, right? Main use of indicators to identify the acid or bases. So general water will be the neutral solution. You can just try. So in order to identify the neutral solution also, we are using the another type of indicator that are synthetic indicators. So these are synthesized in the laboratory, right? This is not natural. We need to prepare in the laboratory, and they indicate the presence of acid base by changing their color. The most common examples which we are using in the laboratories are, first one, pH paper, right? pH paper, then phenolphthalein, another synthetic indicator, then methyl orange, right? Methyl orange, thymol blue is already present, and xylenol orange is also present. So these are the three important synthetic indicators we need to focus here. Clear? Okay, we will be discussing about the pH paper in detail in the last of the class, right? Towards the end of the class, what do you mean by the pH paper? Then you will get an idea. So first one, it is the phenolphthalein, right? Phenolphthalein is another type of indicator which will be having a formula of C20H14O4. No need to memorize the formula here. You just have an idea about the what is the phenolphthalein indicator, right? So what you're observing here, this is the acid solution, right? This is the acid solution, and this is the alkali solution. So in general, this phenolphthalein is having a color of pink color, right? They are pink color, but if you are adding into the acidic solution, they will become colorless, right? They will become colorless. So initially they are colorless, but it is transition to pink within the pH range of 8.2 to 10. So I hope you may have idea about the pH scale, right? There will be pH scale is present. So the pH scale will be having in the variation pH value from 1 to 14, right? So from pH 8 to 14, these are known as the basic solution. And from pH 1 to 7, these are known as the acidic solution. And those substances which will be having the pH is equal to 7 is known as the neutral solution, right? So these phenolphthalein will be showing a pink color with the pH range of 8.2 to 10, right? 8.2 to 10 means they are generally basic solution. Clear? Yes, let us discuss what can we use as a universal indicator, right? So this is the case of pH paper or the pH indicators, right? So here in the case of phenolphthalein, whenever you have the pH range of 8.2 to 10, which means if they are basic solution, they will be having a color of pink color, and if it is having the pH range of 1 to 7 or have the acidic solution, it will be having a colorless. It will not have any particular color. Okay, I hope you understand the color difference of phenolphthalein indicator in acid as well as base, right? Now let us see the another indicator, that is methyl orange. So this is the general formula for the methyl orange. So this is the color for this substance, either orange or red, we can say orange or red. So what is happening to the methyl orange if you are adding to the acidic solution, right? This is our acidic solution. So if you are adding the methyl orange indicator to the acidic solution, it will be turned the color to red color or orange color. Then if you are adding to the yellow, if you are adding to the basic solution, right? If you are adding to the basic solution, it will be turning to a deep yellow color, right? Deep yellow color. And generally, if you are using the neutral pH also, it will be having a light yellow color. So this is the color difference of methyl orange in presence of acid, base and neutral solutions. Is that clear? So based on the color difference, we can identify the methyl orange as an indicator for the acid base. Now another type of indicator is the self indicators. There is no need of any other indicators, right? The substance itself acts as an indicator. Such type of example is the potassium permanganate, KMnO4, right? Potassium permanganate, maybe you may see in the laboratory, right? It will be having a pink color solution, So it acts as an oxidizing agent. We have already discussed, right? What do you mean by oxidizing agent in the first chapter? So it itself undergoing reduction to form a color change of, first it will be having a pink color or the purple color. After reacting, it will be turned to colorless solution upon the complete reduction. So it will be used as a self-indicator. So if you are using any reaction with the potassium permanganate, there is no need for any indicator, right? The KMnO4 itself acts as a self-indicator. It will be changes its color from purple or pink color to colorless. Is that clear? Now here is the answer for your question, Durgeshwar. What do you mean by universal indicator, right? So we can say that the pH paper, right? pH paper, as we already know, these are the mixture of organic dyes and the synthetic indicators, right? These will be containing organic dyes or the synthetic indicators. So it will give different colors to the different pHs, right? It will be giving different colors to the different pH values. So they are known as the pH indicator. In general, they are also known as the universal indicator, right? Because they are more sensitive than other common indicators. That's why they are using as a universal indicator. Durgeshwar, I hope you understand now, right? I'm repeating again. In the case of pH paper, right, they will be containing some organic dyes or colors. So they will be giving different colors with the different pH value. So these are known as the pH indicators or pH papers. And this is more sensitive than the other common indicators like phenolphthalein or methyl. That's why we are calling this as a universal indicator. Now you can see the color difference here, right? So this is our complete pH scale or the universal indicator scale. So what you're observing here, this is our first example of battery, right? Now you can predict in the battery there is any acid solution or basic solution present. pH value is equal to 0, right? pH value is equal to 0. Those indicators are easily give colors with the different pH values. As you can see over here, the different pH value, they will be having different colors. But if you are using, if you are using methyl orange or phenolphthalein, we can say that they will be having any pink color, either pink color or red color, right? We can't predict the pH value for those acids or bases by using normal indicators, right? Again, in the case of litmus paper is also, we can't say that universal indicator, right? Okay, litmus paper, as we already know that in the acidic solution, they will be changing color from red to blue, right? Red to blue and blue to red color changes. But in the case of universal indicator, by knowing the color change, you can exactly identify the pH change. I hope you understand, right, Durgeshwar? So, what about the case of battery? What is the nature of the substance present inside the battery, whether it is an acid or base? pH is equal to 0, right? So is it an acid or base? Yes, it is highly acidic, right? Because it is having the pH value of around 0. So this is highly acidic. So if you are moving from 0 to 7, acidic character decreases, right? Acidic character decreases. So what about the case of stomach acid? Which is the acid present in the stomach? Hydrochloric acid, right? So HCl is the hydrochloric acid, stomach acid, it will be having a pH of 1. General color will be around orange. Then second one, lemon, it will be containing citric acid, right? It is having a pH of 2, almost light orange or yellow color. Then vinegar, as we already know, CH3COOH acetic acid, pH is equal to 3. Tomato, again there will be another acid, right? Tartaric acid is present in the case of tomato, it is pH 4. Then in coffee, caffeine, right? So it will be having a pH 5. Milk, again lactic acid is present, right? So pH is equal to 6. And for water, water is a neutral molecule, right? Water is neutral. It will be having a pH of 7. Now, by changing the pH value, you can see that from 8 to 14, right? 8 to 14, they are alkaline. So you can say that this will be more alkaline, right? Blood is more alkaline. Then baking soda, as we already know, they are basic solutions. Stomach tablet, when we are using the antacid, right? They will be having the basic solution with pH of 10. Ammonia, pH 11. Soap is having pH 12 and bleach is having pH 13 and drain cleaner is having pH 14, right? So this is the color change for the pH indicator or the universal indicator for the different substances depending upon the pH value. Is that clear? So that's all about the indicators part. Now we need to discuss about the different theories of acids, right? The first theory is the Arrhenius theory. So how we can define the Arrhenius theory? Okay, you can just memorize this scale only. There is no variation for the different colors and different pH. Our main aim is to find out whether the substance is acid or base depending upon the pH value or the color change, right? So what do you mean by Arrhenius acids? In aqueous solutions, they are forming. So these are H plus forming, right? So as you can see over here, HX is an Arrhenius acid, so it will be forming H plus. In aqueous solution, they will be giving H plus ion and the X minus ion as the component here, right? Or we can say that HX is water form, hydronium ion, H3O plus ion or the X minus ion. So these substances, according to Arrhenius theory, acids are the substance which will be giving H plus ions to the, okay, H plus ions in the aqueous solutions, right? So these are the common example for the Arrhenius acid given here. HCl, right, hydrochloric acid, which is easily giving the H plus ion, and HNO3 nitric acid, again giving H plus ion. H2SO4 sulfuric acid, right, it is also producing 2 H plus ion. H2SO3 sulfurous acid. Then H3PO4 phosphoric acid, HClO3 chloric acid, and HClO4 perchloric acid. These are the common examples in terms of Arrhenius acids. Now what do you mean by the Arrhenius bases? As we already know, acids are the H plus donors in the aqueous solutions, right? Now what would be the concept of bases? So they will be producing the OH minus ion, right? Hydroxyl ion or OH minus ion. So as you can see over here, MOH is the Arrhenius base, so it is easily forming M plus ion plus OH minus ion in the aqueous solution, right? So what is the limitation of this theory? The common examples are sodium hydroxide NaOH, potassium hydroxide KOH, magnesium hydroxide MgOH twice, right? Calcium hydroxide CaOH twice, aluminum hydroxide AlOH twice, and NH4OH, ammonium hydroxide. These are the common example for the Arrhenius bases, which on aqueous solution, whenever you are adding water to the solution, it will easily forming the OH minus ion or the hydroxide ion, right? Now what will be the limitations of this theory? You have already seen, right? These are forming H plus ions or the OH minus ion. Yes, it is only applicable in the case of aqueous solution, right? Okay, it does not explain the basicity of molecules like ammonia does not bear OH minus, right? Then main, it is applicable only to aqueous solution. For the non-aqueous solutions, if you are taking any other solution other than the water molecule, it is not applicable, right? It is applicable to aqueous solutions only. Then another limitation is that, for example, if any of the substance like BF3 that does not have any H plus atom to produce H plus ion, but it is having the acidic behavior, right? Then if you are taking ammonia molecule, there is no any presence of OH minus ion. Then also they are having the basic character. So this theory fails to explain the existence of these compound as an acid or base. Now what will be the another theory which we accepted after this theory, Arrhenius theory? Our second theory, right? The Brønsted-Lowry acid-base concept. Yes, Brønsted-Lowry, right? So, according to Brønsted-Lowry concept, acid is a substance that is capable of donating H plus ion, right? Or we can say that these are the donor. Similarly, bases are the H plus acceptors, right? So, according to Arrhenius, he said that acids are H plus donors and bases are OH minus donors, right? But ammonia and BF3 failed to explain the existence of acid and bases according to Arrhenius theory. Now, Lowry-Brønsted concept, he is saying like that acids are the H plus donors and bases are the H plus acceptors, right? Base can easily accept the H plus, right? So, let us see the example here, right? So, as we already know, what is the nature of ammonia? Ammonia is a base, right, as we already know. So, when ammonia is treated with water, right, according to Lowry-Brønsted concept, as we already know, base can have the tendency to accept H plus ion, right? So, this NH3 will be accepting H plus ion to form NH4 plus, right? I hope you are getting my point, right? So, NH3 is a base, as we already know in general, right? So, it will be having a tendency to accept H plus ion, so it will be forming NH4 plus ion, right? So, this will be the base and this pair is known as the conjugated acid, right? Conjugate acid. So, according to Lowry-Brønsted concept, they have given one more point, there is a conjugate acid base pair present, right? So, NH4 plus will be our conjugate acid. Similarly, if you are saying here in the case of water molecule, right? Water molecule will be act as an acid in case of base, right? This is act as an acid in case of base. So, acid means they are donating H plus ion, right? So, water will be donating one of its H plus ion to form OH minus ion, right? So, here water is acid, so it will be forming a conjugate base. So, this pair of acid base is known as a conjugate acid base pair. Is that clear how we can find out the conjugated acid and base depending upon the acids and bases present here? Now you can predict the conjugate acid base pair in the case of this pair, right? NH3 plus H2 gives NH4 plus OH minus. So, as we already seen here. So, this is the conjugated, okay, this is the conjugate base and this is the conjugated acid. Now, let us see another example here. Okay, what about the case of this example? Now, I am taking HCl, right? I am treating hydrochloric acid with the water. So, what is the nature of hydrochloric acid? Acid or base? HCl. Acid, right? So, this acid will be having a tendency to lose H plus ion, right? H plus donor. So, it is easily forming Cl minus ion by losing H plus ion. So, this is the acid and the resulting ion will be their conjugate base. So, Cl minus is the conjugate base of acid HCl. Now, what is the nature of water? Water is acid or base here? Because water is forming H3O plus, right, by accepting H plus ion. So, it will be act as a base here, right? Water is act as a base here. So, it will be forming H3O plus ion, right? It will be forming H3O plus ion. So, this will be the conjugated acid of the base water here. Okay, I hope you understand how to find out the conjugated acid and base pairs, right? So according to Lowry-Brønsted concept, acids are the H plus donors, right? Acids are the H plus donors and bases are the H plus acceptors, so that they will be reacting with different compounds to form different acid-base pairs known as the conjugated acid-base pairs. Now we have seen two different examples, right? So in two different examples, you can say that water will be act as both acid as well as base, right? If water is treating with the acid, it will be react as a base. So if you are treating water with the base, it will be having a character of acid, right? Which means that water can act as both acid as well as base. That character is known as the amphoteric nature of water. Is that clear? Is that clear? Now again, in the case of Brønsted-Lowry concept also, they will be having some limitations, right? So not every molecule that is acid or base can lose or accept protons. This is the main limitation of the second theory, Lowry-Brønsted concept, right? Now we will be introducing the another theory that is known as the Lewis acid-base concept or Lewis acid theory. So how we can explain acid or bases in terms of Lewis theory? So moreover the H plus or OH minus ion, we will be taking according to Lewis theory, these are the electron pair acceptor, right? So acids are the electron pair acceptor and bases are the electron pair donor, right? Let's see the example here. So this is our example for BF3, right? BF3. So whenever, I hope you may have idea about to write down the Lewis structures, right? So these dot represents the valence electrons for the different compounds, I mean different elements given here. If you are not aware about the Lewis structures, we will be discussing in the next chapter, chemical bonding, in detail. Acids are not hydrogen acceptor. They are electron pair acceptor. Arush. According to Lewis concept, right? So what you are observing here, this is our BF3 molecule. As you can see over here, 6 electrons are on the central atom. Central atom means this is boron, right? So boron is forming 6 electrons. Boron will be having 6 electrons with the 3 fluorine atoms, so which is known as the incomplete octet, right? So octet, as we already know, any of the compounds will be having the total stability of 8 electrons, but here it is only 6 electrons, which is known as the incomplete octet, right? So it is electron deficient, right? They have very less electrons than the 8 electrons, so it will be easily accepting the electron. So it will be act as a Lewis acid. Clear how they are considered as a Lewis acid? According to Lewis theory, acids are electron pair accepted, right? In the case of BF3 molecule, there is only 6 electrons are present. In order to get stability or to attain the stability, it need to accept one pair of electrons, right? So electron pair acceptors are known as the Lewis acid. So BF3 is an example of Lewis acid. Is that clear? Now the next example is the case of ammonia molecule, right? Ammonia molecule. So what you are observing here, so ammonia will be forming again 6 electrons with the total 6 bonds with the 3 hydrogen atom, right? So one electron is a lone pair here, right? One electron is a lone pair here, which means that it will be having extra electron pair is present, right? So this is known as the electron rich substance. So it can easily donate these electron pair, right? These can easily donate these electron pairs. So these are known as the Lewis base, right? Base have the tendency to donate the electron pairs. Is that clear? Okay, accept means to take electron pairs, right? To gain electron pairs. Now again another example is the case of SF4 molecule, right? SF4 molecule, as we already know, an extra electron pair is present here, so it can easily donate these electron pair, right? So these are the example for the Lewis base. One example is the SF4 molecule. So we will be discussing in detail about to write down the Lewis structures in the chemical bonding chapter. Then you will get the idea how to draw these structures, right? Yes, Irish, according to Lowry-Brønsted theory, what is the concept of acids? They are hydrogen donors, right? H plus donors. Bases are the hydrogen acceptors. So these are the examples. When you are treating Lewis acid and Lewis base together, they will be forming an adduct of 2 electrons over here, BF3 dot NS3, right? This is the reaction between Lewis acid and the Lewis base. Clear? Okay, next class, in the sense next upcoming classes, I will going to discuss the chemical bonding chapter. So again, another example, carbon dioxide is a Lewis acid, right? So when you are drawing the structure for the carbon dioxide, it has easily accept the electron pairs, right? So it will be reacting with water to form H2CO3 as the product here. So this is known as a Lewis acid and Lewis base concept. Now we need to discuss about the different compounds, right? Different compounds formed by the case of these acid, base and salts. Before that, we need to identify what we mean by water of crystallization. So what do you mean by water of crystallization, right? So as you can see over here, this is our compound, that is sodium carbonate decahydrate, right? Na2CO3.10H2. This water molecule that is loosely attached to the one molecule of salt is known as the water of crystallization. So if anyone asks you for the water of crystallization for the Na2CO3 molecule, its answer will be 10, right? 10 molecules of water is present in the case of sodium carbonate. Clear what do you mean by water of crystallization? Okay, for the CBSE part, you can refer till Lowry-Brønsted concept. For the higher level, I am discussing about the Lewis dot theory. Okay, Lewis base theory, right? Lewis acid base theory. So water of crystallization we have already seen. These are the crystal of salts which contain water are the component here. Just giving a few idea about the water of crystallization. Now let us discuss about the some of the compounds, right? First example is the common salt. As we already know, what is the chemical formula of common salt? Sodium chloride, right? Sodium chloride or NaCl is the common salt which is used in our food. So how it is forming, as we already know, as a part of neutralization reaction, right? I am taking sodium hydroxide plus hydrochloric acid. This is a base, this is a base. Sorry, this is a base and this is an acid. This acid and base combine together to form the salt plus water, right? So sodium chloride will be the salt formed by the reaction of hydrochloric acid and the NaOH. So that's all about the case of NaCl. Some more points are given in our NCERT textbook about the uses of sodium chloride. Just refer in your textbook, refer from your textbook. Now we need to discuss about the next compound, that is our bleaching powder, right? Bleaching powder, as we already know. In order to, for the cleaning purposes, we are using the bleaching powder, right? Domestic cleaning purposes, we are using the bleaching powder as the component, right? So what is the chemical formula of bleaching powder? CaOCl2, right? Otherwise, it is also known as calcium oxychloride. CaOCl2, calcium oxychloride. So as you can see over here, this is a white powder, right? White colored powder is known as a bleaching powder used for the cleaning purposes. Now, how it is formed? What is the preparation method for the calcium oxychloride or the bleaching powder? So, as we already know, right, this is the slaked lime. If you are taking slaked lime or the calcium hydroxide with the chlorine, right, chlorine, it will be forming CaOCl2 plus water. So this is the simple method of preparation of bleaching powder in the industrial purpose. Clear? Slaked lime and chlorine treated to form CaOCl2 plus water, right? Clear? Now these are some of the properties of bleaching powder already given in your textbook. And this is the white amorphous powder with a pungent smell of chlorine. Then it is considered as a mixed salt of calcium chloride and calcium hypochlorite. So we can generally write it as CaCl2 plus CaOCl twice, right? If you are asking about the chemical formula of bleaching powder, you can just give the CaOCl2 as the chemical formula, right? No need to confuse here. In general, it is the mixed salt of calcium chloride and the calcium hypochlorite. Now, on long standing, bleaching powder reacts with carbon dioxide and loses chlorine, right? So this is our bleaching powder. If you are treating with the carbon dioxide for the long term, it will be forming calcium carbonate, right? Calcium carbonate plus chlorine. Now the another property for the bleaching powder is on dissolution of water. If you are dissolving this calcium oxychloride or the bleaching powder in water, it will be forming slaked lime plus HOCl, right? HOCl. In the case of these substances, we need to focus on the different reactions, right? So as we already know, bleaching powder will be having different properties, right? Just like what is the product formed when they are treating with water or their treatment with carbon dioxide, right? So you can expect this type of questions from that part for the bleaching powder, sodium chloride, washing soda and baking soda. So I hope you understand, right? So they will be forming hypochlorous acid. HOCl is known as the hypochlorous acid and HCl is the hydrochloric acid, right? So each and every reaction for the bleaching powder as well as all the given salts in the textbook is very important. You can expect questions from there. Now the reaction of bleaching powder with dilute acid, right? So if you are taking the dilute acid of H2SO4, it will be forming calcium chloride plus calcium sulfate plus HOCl. And if you are taking again in the case of HOCl, hypochlorous acid, it will be forming HCl plus nascent oxygen. This free oxygen is known as the nascent oxygen. Now the next compound which is given in your textbook is the plaster of Paris. As we already know, right? If you have any crack in your bones, the doctors will be suggested to put in covering of plaster of Paris, a white color substance, right? This is known as the calcium sulfate hemihydrate. Their chemical formula will be CaSO4.12H2O. Clear? This is the chemical bond in between the calcium sulfate or the calcium sulfate hemihydrate. So you need to get an idea about what you mean by plaster of Paris, how we are preparing the plaster of Paris, right? So this is the method of preparation of plaster of Paris. CaSO4.2H2O, right? So what is the water of crystallization here? In the case of CaSO4.2H2O, water of crystallization. The number of water molecules present is known as the water of crystallization, right? So in the case of this molecule, the water of crystallization is equal to 2. So this substance is known as the gypsum. Clear? So if you are treating the gypsum, it will be easily forming the semihydrate of plaster of Paris. So in the case of plaster of Paris, the water of crystallization will be equal to half H2O. Is that clear? This method of preparation for the plaster of Paris is very important, and many of you may confuse or made mistake in the case of chemical formulas of gypsum and in the case of plaster of Paris, right? Plaster of Paris is half H2O and gypsum is 2H2O. Okay, I hope you understand how to prepare the plaster of Paris from the gypsum, right? So this is the method of preparation. Now we need to focus on the properties of plaster of Paris, right? So plaster of Paris is a white powder. Whenever it is mixing with water, right? If you are mixing with the water, it is easily forming the gypsum. Gypsum is again another white color substance. Is that clear? So that's all about the part of plaster of Paris. The next compound which is given in our textbook is the washing soda, right? Washing soda. So what is the purpose of washing soda? The name itself, right? They are using for the washing purposes. So it is a basic salt, usually contains sodium, usually obtained from the sodium chloride, and its formula will be Na2CO3.10H2O, which means that water of crystallization will be equal to 10 for the washing soda. It is again a white color substance, right? White colored powder. This is also known as sodium carbonate decahydrate. Deca stands for 10 water molecule. Hydrate means water molecule. Deca stands for 10 water molecule. Now how we can prepare the washing soda? They are prepared by a process of known as Solvay process. Let us see what is the reaction in between the Solvay process, right? So this is our sodium chloride, right? Sodium chloride. It will be treating with calcium carbonate, right? Calcium carbonate. So what it will be forming? It will be undergoing a double displacement reaction, double decomposition reaction, right? Double decomposition. So it will be forming Na2CO3, sodium carbonate plus calcium chloride, right? Okay, I hope you are getting my point, right? So in the case of sodium chloride, it will be reacting with calcium carbonate to form NO2CO3 plus CaCl2. Then these 10 water molecules again react with the Na2CO3 to form Na2CO3.10H2O. This is the same reaction given in your module or the textbook. Now what are the properties of washing soda? So these type of reactions are very important in your examination point of view. It is a white crystalline substance, right, that loses water easily. So these Na2CO3.10H2O on heating, it is easily forming Na2CO3.9H2O and are easily forming the Na2CO3.H2O, right? Clear? Yes, memorizing the reactions is very important. You can expect this type of questions. Your board examination point of view. Okay, towards the end of the chapter, we are going to discuss about the salt preparation, right? How we can predict the acidic or basic salt. So, again, I am just giving a brief idea. If you are heating the Na2CO3.10H2, it will be easily forming sodium carbonate plus 10 water, already given in your textbook. Now let us discuss about the case of neutralization reaction, right? So what do you mean by neutralization reaction? As we already know, right? In the case of acid and base, they are reacting together to form the salt plus water, right? Salt plus water. So these are the examples, right? So NaOH plus HCl is forming NaCl plus water. So what is the nature of sodium hydroxide? Whether it is a strong base or weak base. NaOH is strong base or strong base or weak base. So both are strong acid and strong base, right? So if you are treating with strong acid and strong base together, we will be getting a salt with nature of neutral salt. Again, in the case of this also, KOH is a strong base and HNO3 is the strong acid. So it is again forming a neutral salt of KNO3 plus water, right? Another example is NaOH plus H2SO4 gives NaHSO4 plus H2O. Again, if you are taking 2 moles of NaOH, it will be forming Na2SO4 2H2O, right? Depending upon the concentration of the base used, it will be having different composition, right? Now let us see how to predict the salt formation, whether it is a strong, acid salt, basic salt, or the neutral salt, right? So there will be 1, 2, 3, and 4 different reactions happening here: strong acid, strong base, weak acid, strong acid, weak base, and weak base, weak acid. So this is very important. So strong acid, strong base, right? We have already seen. If you are taking NaOH as a strong base and HCl as a strong acid, it will be forming a neutral salt. Clear? So these are the common examples. It's very important. If you are taking strong acid and strong base together, we will be getting a neutral salt. Now what about the case of strong acid, strong base, right? Okay, as we already know, these are forming the, okay, if you are having the concentration of acid is, whether it is compared to, if it is having the concentration higher than to the base, we can say that it will be forming an acidic solution. Let us see by examples, right? So what about the nature of this salt formed here? NaOH plus CH3COH, right? As we already know, this base is a strong base, right? Sodium hydroxide is a strong base. Then what about the case of acetic acid? It will be a weak acid, right? It will be a weak acid. So depending upon the strength of acid or base, we will be forming different salt, right? So CH3CONA is a salt which is having the strength of base here. So it will be a basic salt. Is that clear? If you are having strong base and weak acid together, we will be getting a salt which is having the basic nature. Clear? This is another example in the case of NH4OH plus HCl, right? HCl is a strong acid and NH4OH is a weak base, right? If you are mixing weak base and strong acid together, the resulting salt will be having a nature of acid, right? Okay, I hope you understand how to find out the nature of salt, right? The last case is the case of weak acid and weak base. So it will be forming either acidic, basic or neutral depending upon the dissociate constant value. So once we are discussing about the Ka value in detail in the grade 11 chapter, we will get an idea about that, right? So in general, we need to focus on the strong acid, strong base concept, weak acid, strong base concept and the strong base and weak acid concept, right? So this is a general summary of the formation of salt, right? If you are taking strong acid and strong base, they will be forming neutral salt. If you are taking strong acid and weak base, they will be forming acidic salt. This is the example. And if you are taking weak acid and strong base together, they will be forming a basic salt. Okay, I hope you understand. Okay, that's all about from my side for today. We have already completed the acid, base and salts chapter, right? I hope I have completed almost all the important topics from the acid, base and salt. So just refer the previous year questions for solving the questions for this chapter. And there is a general reminder about the SCORE exam. Sri Chaitanya Academy is providing you a SCORE examination. It is an international level talent examination. It will be conducting on September 28 and October 12. So you need to register now for the examination registration, which will be available in our website of Sri Chaitanya, score.com. You can register there. And it is a big opportunity. You will be getting in NASA trip, excited gadgets as well as the up to 100% scholarships are given here, right? It will be applicable for students from grade 3rd to grade 11. So you can register now only. Link will be provided in the description. You can register in the website given there. Okay. I hope you guys enjoyed the session. If you really like the session, hit the like button, subscribe our channel, share this particular session to your friends also. Okay, Arush, in order to memorize the reaction, you need to focus more on the reaction, right? So try to revise in a daily basis, try to write down the chemical reactions in notes, right? And only we can memorize these reactions, otherwise we will be forgetting. So thank you so much all of you. See you in the next class. Okay, if you want to get the session PDF, you will get from our Telegram channel. It will be available in the Telegram channel. So see you in the next class. There is a small time change from our classes tomorrow. Live class will be from 4 to 5. So thank you so much all of you.